welcome to This Explainer. Today, we're decoding exactly how a CPU works. Basically, the secret sauce you need to absolutely crush your computer science final exam. So, if you've ever found yourself wondering what actually makes your computer run fast, well, you're in the exact right place.
Okay, let's dive right into this by starting with an everyday question, just to kind of anchor our understanding before we get to the abstract stuff. What makes a racing car fast? Like, really think about it for a second.
You inherently know that a car's speed isn't just about throwing a massive engine in there, right? It's a whole combination of physical and environmental factors working together. I mean, you've got the horsepower, sure, but there's also the grip of the tires, the weather out on the track, the driver's skill level, and the aerodynamics. All of these things dictate the overall speed in a race.
And honestly, this brilliantly illustrates our core concept. Because just like that racing car, a computer's CPU, the central processing unit, doesn't rely on just one single magical thing to go fast. Its overall speed and efficiency are determined by multiple critical components, all working in tandem. Specifically for your exam, we're swapping out horsepower, tires, and weather for clock speed, cache, and course.
Here is our strict study guide playbook for today. 1. Clock speed. 2. The cache. 3. CPU cores. 4. Single versus multi-core architecture. And 5. Exam terminology review.
Section 1. Clock speed.
Now, for your final exam, you need to remember this strict definition. Clock speed is the number of instruction cycles per second a CPU can execute, measured in hertz. Basically, the faster that internal clock ticks, the quicker your computer fetches and executes its instructions. To put this into perspective, 1 billion. A single gigahertz represents 1 billion operations per second. Think about that. If you try to count to a billion out loud, it would take you over 30 years. Your CPU? It does it in 1 single second. Modern processors operate in multiple gigahertz, meaning they are chewing through literally billions of instructions in the blink of an eye. It's totally mind-blowing when you really think about it.
Section 2. The cache. Make sure you write this one down. The cache is essentially a hyper-fast temporary local storage area built directly inside the CPU itself. And why is it there? Well, to save the CPU from wasting precious milliseconds fetching the exact same data from the much slower main memory over and over again. Every time the processor fetches an instruction or writes data to the main memory, it keeps a super convenient copy right there in the cache.
Think of this process like sitting at your desk. Step 1. Checking the local cache. That's exactly like checking your own top drawer for a file. Super fast, right? Step 2. If the file is missing, you have to actually get up and walk to a massive filing cabinet all the way across the room. That's your slower main memory. Step 3. Once you grab that file, you leave a copy right on your desk, in the cache, so you definitely don't have to walk across the room next time. Avoiding that long trip across the room as much as humanly possible is what makes the CPU incredibly efficient.
Now, you might be wondering, why not just make the cache huge and get rid of main memory entirely? Well, cache space is strictly limited and frankly incredibly expensive to manufacture. But here's the secret. We actually only need a relatively small amount of cache to notice a massive leap in overall CPU performance. That highly localized efficiency really does go a very long way.
Section 3. CPU cores. So the absolutely crucial point here for your test is that a core isn't just a tiny fraction of a processor. A CPU core is an entire self-contained processing unit. It has its own registers, its own ALU, its own accumulator. And because of this, a multi-core processor actually has the raw physical hardware to run entirely different programs at the exact same time.
Section 4. Single versus multi-core architecture.
While most people point to that physical square chip plugged into their motherboard and just broadly call it a CPU, that isn't always technically accurate. If that single physical chip contains a multi-core setup, like a quad-core, with 4 separate processing units and some shared cache, the correct term you want to use to impress your examiners is a chip multiprocessor. It's literally multiple CPU cores embedded into one single physical chip.
Let's look at the exact trade-offs here. A single-core setup handles one main task at a time, but it works at absolute maximum efficiency because, well, it never has to wait on anyone else. A multi-core setup, on the other hand, can juggle many simultaneous programs, but it actually loses a little bit of raw efficiency. Why? Because those multiple cores have to constantly talk to each other to stay in sync. Plus, honestly, a lot of software programs just aren't designed to make maximum use of multiple cores quite yet.
Oh, and here's a quick pro tip bonus fact for you. Modern gaming PCs and consoles completely avoid bogging down their main multi-core processors. Instead, they offload massive, specialized tasks to dedicated graphics and sound cards. By letting those specialized chips handle the heavy visual and audio work, the main CPU is freed up to run the game's core logic at lightning speed.
Section 5. Exam Terminology Review.
Let's rapid-fire the specific vocabulary you absolutely need to know. Hertz measures your instruction cycles per second. A gigahertz is 1 billion of those cycles. The cache is your hyperfast local storage. A CPU core is a complete independent processing unit. And a chip multiprocessor embeds multiple cores right onto one physical chip. Having these definitions locked in your memory is exactly what will secure you those top marks on test day.
As you wrap up your studying, I want to leave you with a bit of a provocative thought. What happens to computer science when we can no longer physically fit more cores or more cache onto a single microchip? We are rapidly approaching the physical limits of hardware engineering, and solving that roadblock, well, that's the next great frontier. Think about that as you review your notes. Thank you so much for joining me for this explainer, and hey, best of luck on your exam. You've got this.